Hello, everyone. I hope you are all doing well. On behalf of SP Egypt Young Professionals, I would like to welcome you all to today's session. My name is Ahmed Haytham. I am a fresh graduate petroleum engineer from Suez University and the e-mentoring head at SPE Egypt YP, and I will be your moderator for today. Before we start, I would like to remind you to please drop your questions in the Q&A section below, and please keep the chat box professional and ethical. Now, without further ado, please give a warm welcome to Engineer Ahmed Samir, who will be giving us the second session of our short course that consists of 3 webinars on hydraulic fracturing. Engineer Ahmed Samir is a qualified frac engineer with more than 12 years of experience in oil and gas industry, with extensive experience in all kinds of frac techniques, in addition to experience in completion design for oil and gas wells. This includes over 100 frac jobs performed using all frac technologies such as highway, foam frac, foam highway, clear frac, rod chip, proppant, and furthermore, and fracturing of extensively deep high temperature formations. He is an author and co-author of many technical papers published at national and international conferences. Also, he is a qualified stimulation training instructor. Engineer Ahmed Samir is holding both bachelor degree and master degrees in petroleum engineering from Cairo University. His current position is the Petroleum Engineering Department Manager at Agiba Petroleum Company. Engineer Ahmed, thank you so much for coming, and the mic is yours.
Good night, everyone. Hi, everybody. Yesterday we stopped at the fracture fluid, and we explained yesterday the gelling agent and its classification. Today we are going to start with fracture fluid additives, types, and its function. Okay. What is the additives of the frac? The additives of frac is used to modify the fluid behavior of the fracture fluid. What we are using as a fracture fluid additives is the buffers, biocide, breakers, clay stabilizer, fluid loss additives. This is the most common used additives in the fracture fluid. However, that we have another additives that is not commonly used. Additives is friction reducer, temperature stabilizer, and surfactant, non-emulsifying agent, and the proppant flowback control. We will start with the surfactant. Surfactant is or surface active agent is defined as a surfactant is a material which at low concentration absorb at the interface between two immiscible substances. The surfactant become involved in the interface and lower the amount of energy required to expand the interface. This means what? This means that we are using the surfactant to reduce the required force to move one fluid at the surface of the rock. So what is the reason of that? We adding the surfactant to the fracture fluid. We are using the surfactant to the frac fluid for the following reason: to perform stable foam frac fluid that we have. If we are using nitrogen with the foam frac fluid, to create what we call a nitrified frac fluid. This frac fluid is called foamed frac fluid. To have this foam frac fluid stable and avoid escaping of nitrogen from the gelling agent, because we are bumping the gelling agent in combine with the nitrogen to create a foamed fluid. To avoid the escaping of nitrogen from the gelling agent is we are using the surfactant. Also, we are using the surfactant to stabilize the water external the emulsion in polyemulsion fluids. Okay. Also, we're using the most common reason to use the surfactant is to perform easy fracture fluid clean out. So what we said in the beginning, that the surfactant is fluid that we are used to reduce the interfacial tension between the liquid molecules and the surface of the rock. So once we reduce this interfacial tension, this means what? This means that it is easier to move the fluid from the formation, the bumped fluid, the fracture fluid bumped into the formation. This this will result in more easier recovering for the fracture fluid that you bumped in the formation. So you will reduce the tendency of the fracture fluid to damage the reservoir, because we are using the gelling agent itself. It is the gelling agent is a polymer, and the polymer have a long chain, and we are using the breaker to break these chains and reduce the size of the molecules. However, that even after using the breaker, still we are facing problems in recovering the fracture fluid, because of that we said the fracture fluid is damageable. So in order to increase the chance to recover this frac fluid from the formation, we are using the surfactant. So we have also, for the surfactant, you have to know that two terms. The first one is hydrophobic surfactant and hydrophilic surfactant. Hydrophobic surfactant is oil soluble, so it is soluble in the oil, and we use hydrophobic surfactant to enhance the production of oil. And hydrophobic surfactant is the surfactant that water soluble, and this is the commonly used with the fracture fluid, because we are using the fracture fluid as a water-based fracture fluid. Also, for the reason that we are using the surfactant, is the controlling the wettability, because if we are going to use one fluid additive that is going to change the wettability of the reservoir, we need to use an agent that controlling the wettability. Also, to prevent and break the water flux. The water flux is called, its definition is what? It is water that is occupying the space of the pore spaces inside the reservoir rock, and its interfacial tension is high enough to prevent any oil from displacing this water and pass through these pore spaces. So the water plug is water is remaining constant in its place and preventing oil from moving through these pore spaces. So to remove this water plug, you need the surfactant to reduce the surface tension of this water, surface tension between this water and the rock grain, and to be easy to displace this water, and the oil will pass in these pore spaces. Also, we use the surfactant to suspend the fines to improve the carrying capacity of the proppant. We discussed also the foam case. Also, we using the surfactant to reduce the sludge tendency to be formed. Also, we use the surfactant to treat the asphaltene if there is possibility to form asphaltene, because the asphaltene is formed during the fracturing job, because we are cooling down the formation after pumping the frac fluid, because the frac fluid is pumped inside the reservoir at low temperature, lower than the reservoir pressure. So we are cooling down the reservoir. So there is possibility if the oil inside the reservoir have tendency to format asphaltene. So we will, with cooling down with the frac fluid, there is possibility to formate to precipitate asphaltene from the oil, especially heavy oil. So we are using surfactant to reduce the tendency to format asphaltene. Okay. So the next fluid additives is non-emulsifying agent. We are using the non-emulsifying agent to prevent or to break the emulsion formed between the frac fluid and the formation fluid. What is the risk of formatting emulsion between the frac fluid and the formation fluid? We know that the emulsion have a higher viscosity than the two fluid participated in this emulsion, which means if we have two fluids like oil and the frac fluid, both of them have a viscosity. If we create an emulsion between these two fluids, the resulted emulsion will have a viscosity higher than the highest value of the viscosity for any one of them. This means what? If you increase the viscosity of the formatted emulsion, you will result this high viscosity will result in reduction in the production rate, and it will be effective significantly on the well deliverability, because this fluid with this this emulsion with this high viscosity will be remaining inside the pore spaces and prevent the hydrocarbon from moving through these pore spaces. So we are using the non-emulsifying agent to break this emulsion once it's formatted to avoid the reduction of the well deliverability.
Engineer Ahmed,
Yes.
sorry to interrupt you, but I think there is something with the window screen.
Yes.
So can we close the sharing screen and reshare it again?
Okay.
Thank you.
Not this one.
Okay, perfect.
No, but not this one.
Okay, no problem. Take your time.
This good?
Yeah. You can just make a full screen.
It is full screen, yes? Or 1 second. Stop. Like this, okay?
Perfect. Thank you so much.
Okay. Clay, then we will start with the clay stabilizer. Why we are using clay stabilizer? Easy is we are using clay stabilizer to prevent the clay from swelling and migration. What is the problem of the clay swelling? If your reservoir rock is containing laminated clay or dispersed clay. Laminated clay means layers of clay in between the sand layers, or dispersed clay is dispersed between the grains and inside the pore spaces. If this clay is swelled, because the clay is swelled normally by the water. So if your fracture fluid resulted in clay swelling, this clay will swell where? Will swell inside your pore spaces. This means what? This means that your pore spaces will be occupied by clay, swelled clay, instead of be clear to pass the hydrocarbon through. So it is very critical point is to maintain the pore spaces clean and to avoid any clay swelling. We have here some of the clay types, which is kaolinite, elite, charoite, cementite, and mixed layer clay. We have here the clay control methods is anionic neutralizers, and this is the most common used in the fracture, or the organic barrier. In the organic barrier, we are in the anionic neutralizers. What we are using the ions that charged with charge reverse of or opposite of the charges of the clay ions. This means what? This means that these ions in the clay stabilizers will attach themselves to the surface of the clay ions or clay molecules or clay particles. So this will result in a barrier between your water or the water-based frac fluid and the surface of the clay. So this will prevent direct contact between both of them. So with this way, you are stabilizing or preventing swelling of the clay. There is another way is organic barrier. Organic barrier is working like that. The organic matter create a barrier between. It is the same idea, but instead of ions, it is organic material that is attached itself to the clay surface and prevent direct contact between the water and the clay. Biocide and how it's work. Biocide is bacteria and how it is worked by bacteria generated enzymes. Enzymes are used as specific chemical injection, chemical reaction. We are using the bacteria as a breaker, because the bacteria is creating enzymes, and the enzymes is one of the type of the breakers that we can use. But the problem of bacteria and the enzymes as a breaker is this sensitive to the temperature. Also, we are using the biocide to preventing any organism to be exist inside the frac fluid, and we put the biocide inside the tanks before filling with water, because in case that we are not using biocide, we said that the bacteria is creating enzymes, and the enzymes are working as a breaker. So if you have bacteria inside the water that you are going to use for the frac fluid, this may be resulted in early breaking for the gelling agent. So we are using biocide to avoid existing of the bacteria inside the frac fluid and its enzymes that is affecting on or maybe break the cross-linked gel. This is what we was discussing here, the elimination of degradation due to bacterial action and protect the formation from bacterial growing. Also, because of in some cases that when we are using when we are pumping bacteria inside the reservoir, in some cases some of the bacteria are using the oil or the hydrocarbon to create, it is used to break decay the oil or the hydrocarbon, and one of the byproduct of this action is H2S. So the bacteria is resulted in exist of H2S inside the reservoir, and H2S is very harmful in terms of corrosion. So it is important also to use the bactericide or biocide to preventing of pumping bacteria that is creating H2S inside the reservoir. The biocide is not necessary in oil-based fracture fluid because the bacteria is usually not exist in the oil-based fracture fluid. Next additive that we are going to discuss is the puffer. Puffer used to maintain the desired pH value. What is the chemical that we are using as a puffer is the weak acid or promote hydrations. What is the function of the buffer? As we discussed yesterday in the crosslinker, the borate crosslinker need specific range for the pH value. So after you collecting the water and create the linear gel before pumping the crosslinker, you are measuring the pH value. Once you get the pH value, you need to check it is within the range of suitable range to create the crosslinking gel for the crosslinker to work or not. In case that you found the range is not suitable, so you need to use a buffer to reduce or increase the pH value to be suitable for the crosslinker to work. One of the fluid additives is the fluid loss additives. The fluid loss additive is used to reduce the losses of the fluid into the formation. So what is the main effect? When we are going to discuss the frac design, we will talk about the term of the fluid efficiency. What is the meaning of the fluid efficiency? Fluid efficiency means that you are creating frac. This frac have a certain volume, correct? So this frac, when it has a certain volume, and you are pumping a volume of the fracturing fluid. So if you calculate the fracture volume and divide this fracture volume by total fluid volume that you pumped, you will get the fluid efficiency. This means what? The fluid efficiency in another term, it is the volume of the fluid lost inside the reservoir compared to the fracture fluid remaining inside the frac itself. Okay, so the fluid loss additives is very important for the term of the fluid efficiency. Also, it is have a direct contact to prevent the early screen out, because the term of the fluid efficiency has a direct relation to the early screen out. Because of what? Because of the following. Assuming that you are pumping 500 barrels of the frac fluid and your frac volume is 250 barrels. This means what? This means that you are assuming that you will lose 250 barrels inside the reservoir and 250 barrels were remaining inside the frac to create the frac itself. This means the fluid efficiency is 50%. Assuming that the fluid efficiency is less than the 50%, assume it is 30%. This means what? This means that your created frac will be less with this 20% that you will going to lose inside the reservoir. This means what? When you are starting to pumping the proppant you are designed to fill this volume of frac. Once you pumping this volume is reduced. So when you start pumping of proppant, the proppant will fill the available space, and the remaining will not find any space for placement. So this will result in early screen out. So the fluid loss material are used to reduce or improve the fluid efficiency, and by the way, reduce the chance to have early screen out. So we are using the fluid loss additives. We can pump it during the bed. This type is called inert particles. Inert particles mean what? Means that particles have a bigger size, bigger than the size of the pore spaces. So once it in direct contact with the frac face, it is stopped at the frac face and preventing fluid to pass from these pore spaces inside the reservoir. But this type of inert particles are used only during the pumping of the bed. There is another type of fluid loss additives called oil soluble particles. Oil soluble particles was designed to be soluble in oil, not water. This will give you the advantage of once we performed the frac job and succeeded to place the proppant in place. Then we will start the unloading to recover the frac fluid, and then the oil will be in direct contact with these particles. Once it becomes in direct contact with oil, it will start to degrade and be soluble. So it will disappear, and you will gain the higher remaining permeability after it become soluble. However, that for inert particle, it will not be soluble either in water or oil. So it will remain there and will reduce the remaining permeability of your frac. There is another type of fluid loss additives is emulsions. Emulsions, as we said, the emulsion have a higher viscosity than the post fluid used to create this emulsion. So this means what this emulsion, once it is in direct contact with the frac phase, it has a high viscosity and it will not easy to pass inside the reservoir rock. But it have a side effect that emulsion is not easy. This emulsion is not easy to break or to recover. So you need to pump a batch of emulsion breaker to break this emulsion and recover this fluid pumped as a fluid loss additive. Friction reducers. Friction reducers are usually used to reduce the friction inside the frac string, and these are usually used for fracturing in deep wells to reduce the wellhead pressure, the fracture pressure during the activity, and reduce the required horsepower during the pumping, the equipment rating during the pumping. Okay, temperature stabilizers are used to prevent degradation of the fracture fluid at temperature above 200 Fahrenheit. Temperature stability depends on the polymer and the pH value and the presence of the breakers. Okay, we will discuss here the breakers. Breakers type. We have different type of breaker. We have the degradable polymers or oxidizers. Oxidizers are used. This is commonly used as a breaker in the oil market, and are used as a powder or as a liquid. It can pump it as a powder or as a liquid. It is used to undo the crosslinker and break the bonds between the polymer chains. It is guaranteed the maximizing the viscosity reduction of the fracture fluid to be more easy to recover and reduce the potential of damage by the frac fluid. Okay, we have the breaker are used to reduce the viscosity for clean up quickly, to degrade the fluid, reduce proppant bag damage. Okay, for water-based frac fluid, as we said, we are use oxidizers, or we can use enzymes, as we explained previously that enzyme can break the bond between or chain of the gelling agents. Also, there is breaker aids. Oxidizers are used to break. This is a derivative that we will discuss yesterday during the explanation of frac fluid or gelling agent types. The oxidizers are used to break these bonds here and here to break the chains and reduce the viscosity of the frac fluid. There is another type of the breaker is called the encapsulated breaker. This is a new technology used coating, and inside this coating the oxidizers, the breaker is existing. Once the problem of using the breaker is the breaking time, because if you are using the breaker and bumping the breaker, you should calculate the breaking time, because if there is the breaker is activated early, it will result in early screen out, because the proppant is carried by the high viscous fluid. If you break this viscosity early, the proppant will start settle down and you will get a screen out, early screen out. So also, if you delay the time of breaking so much, so you will take so much time waiting for the frac fluid to break or to the breaker activation, then you can proceed with your clean out job. So the time of breaking is critical. So to solve this problem, encapsulated breaker is introduced as a new technology to use coating material. This coating material is break, and the oxidizer is coming out of this coating once the fracture fluid is closed. Fracture is closed. Once the fracture is closed, there is high stress applied at this breaker particles, and it is come out of its coating, and it directly after it's come out, it go for interaction with the frac fluid, and it is resulting in breaking for the gelling agent. This is the idea of the encapsulated breaker. Here. After the forces is applied on the coating, so the breaker is activated. Here the enzymes are highly specialized. Enzymes also are used as a breaker, as we said, but the limitation for the enzymes is the temperature limit, because as the temperature increases, the enzyme itself become unstable. So the enzymes can be decayed at high temperature. So at this time, if you didn't calculate carefully that the effect of temperature on enzymes, it may be decayed, and there is no action for breaking at this time. So it is not usually used the enzymes in high temperature, but it is in low temperature it can be very effective. What is the enzyme? The enzyme is composed of several amino acids. Okay, and this amino acid is from the carboxylic acid groups. Okay, these enzymes are attacking the breaking bond between, or weak bond interaction between enzyme and the bond between the molecules inside of the chains of the polymer. Okay, also we should understand that the pH value also is an important factor for the enzymes, also because it is very sensitive to pH value. So for acidic environment, the enzymes also will be decayed. So you should it have a more have a constraints more than the normal oxidizers as a breaker. Okay, we will discuss now the proppant properties. Proppant is defined as a material that used to prevent the created fracture from closing on itself. So the proppant is formed from ceramic material, and its main function is to prevent the frac closing against itself. It should have high permeability. High permeability is granted by well sorting. Well sorting mean what? Well sorting mean that we have a close range for the particle size. So if we have this well sorting, we will have a good permeability for the fracture. So once the frac close against high permeable and conductive material, this creating a high way for the fluid to pass through it from the porous spaces across the frac face itself. So to granted a good characterization for the material that are going to fill the fracture, we should have the following. It should be crash resistance, which means it have a high strength. Also, it is slightly deformed after applying stress on it to avoid, because if the shape of the proppant changes from spherical shape to or deformated from spherical shape to another shapes, this deformation will reduce its permeability. Also, should be compatible with fluid system. It should be inert and not react with either the formation fluid or the frac fluid. It should be low specific gravity and also should have no flow back. It should not be returned back or produced again with production. Have no impediment, chemical resistance, and it is available, and also it should be cheap, cost effective. Okay, so we have different materials that can used as a material that fill the frac. First during the early fracturing job, sand was using as a material, but sand have a closure pressure less than 6,000 psi. So in the higher closure stresses than 6,000 psi, the sand will start to crash. So if it is crash, it will result in reduction in the conductivity of the fracture. So then intermediate strength proppant and high strength proppant should be used instead of the natural sand. We have a different type of the sand. It's called resin coated sand. Resin coated sand have the advantage of two things. First one is when we coating the sand with the resin, it attaches the sand particles to each other. This will reduce the possibility for this sand to be flow back and return it to the well pour with the production. Also, it will increase its closure resistance up to 8,000 psi. But also it have a side effect. The side effect of using the resin coated sand is the reduction of the conductivity of the fracture, because of the resin is occupied some of the spaces between the sand particles. So in order to overcome this problem, we are using intermediate and high strength proppant and intermediate strength proppant and high strength proppant. The proppant is fabricated from ceramic material, and as we said, have a special range of the particle size, and its sphericity is guaranteed by the testing. Okay. The proppant physical properties is strength. As we said, the grain size and the grain size distribution have a certain grain size distribution. If we said that the proppant 20 by 40, 20-40 proppant, this means what? We are measuring the size of the proppant by the mesh. So if we have mesh has 20 open per each inch. This means this mesh size called 20. If we have 20 mesh open within the square inch, this mesh size called 20. And if we have 40 mesh open inside the square inch, this mesh size called 40. This means what? If we said it is 40 mesh size, we have this mesh will have a smaller open inside this mesh. The 20 have a bigger opens. So the proppant, if you add a proppant sample from the top, your top will be the 20 mesh size. It will pass all the quantity of the proppant, and all the quantity will stop at the 40 mesh size. This is what we call 2040. And similar expression is 1630 proppant. Okay, this is how we distribute the particle size of the proppant. Also have a controlling on the quantities of fine and impurities inside the proppant, and the roundness and sphericity of the proppant is guaranteed. Also, the proppant density is measured and is controlled. This is the effect of the proppant distribution on the conductivity. If we have one size distribution, the pore spaces between the particles will be bigger than if we have an even distribution like this situation. So when you have well sorted proppant and its size is have a well sorting, you will have a better conductivity. Because of this, we are using ceramic proppant. But for the natural sand, if you are going to use natural sand, you will spend a lot of money for sieving this sand to get the required distribution for the particle size. And even if you get correct particle distribution, the sphericity and the roundness of the particles of the sand for sure will not be comparable to the ceramic proppant. What is the concept of the roundness and sphericity? Roundness and sphericity, a measure of grain curvature. Round and small size grain eventually distributed stress resulting in high strength. So the good rounded shape, in addition to it will increase the conductivity. Also, it will allow the grain particle to hold higher stress than the normal sand particles. Okay, we have also the proppant density. The proppant density has an effect on the proppant transport and placement, because as the proppant density increase, its tendency to be settled from the cross-linked gel will increase. This result will resulted in poor placement inside the fracture itself. Okay, this is what we was explaining this point. The high density proppant are more difficult to be suspended inside the frac fluid. Okay, so you should select your proppant density to be suitable with the cross-linked gel that you are going to use. What is affecting on the conductivity? Conductivity is affected by closure stress, because the closure, the fracture conductivity have a reverse relationship with the closure. As the closure increase, the conductivity of the fracture start to decrease. Also, we have the embedment. Embedment is called what? If you see here, this, if we assuming this rock, and this is a proppant inside between the two sides of rock inside the frac, the embedment of the proppant is called this. If we have the probant have move inside the rock itself, so the formation start to enter between the pore spaces here, between the pore spaces inside the probant pore spaces inside the frac. So as this impediment increase, it reduce the conductivity of the fracture itself. Okay, this is the classification of the probant. We have the sand, resin coated sand, and the intermediate and high strength and high strength probant, as we said. This is properties of the intermediate strength probant. It is low density. Effective strength limit is 10,000 psi. Its specific gravity is 2.7. This is the low density probant. Medium density probant effective strength limit is 10,000 psi and its specific gravity is 3.2. High density or high strength probant, its strength limit is 15,000 psi and the specific gravity is 3.49. So this is the test that we are using to evaluate our probant. First test is sampling and splitting. We have a density test, sieve analysis. This is for the sieve analysis. We should have 90% of the probant should be between the designating sleeves size and round and sphericity. This means what? If you have a sample of the probant, 90% of this probant should pass from the first sieve and not pass from the last sieve. This is the test of the sieving analysis. Also, there is acid solubility test for the probant. Acid should dissolve less than 2% of the probant. Also, there is crash resistance test that we are taking a sample and applying compression force on this sample, then repeat the test of the sieving analysis. Because when you applying compression force on the probant sample, it will start to crash some of the probant. Once the probant particles crashed, the sieving analysis result will be changed. So to pass this crash resistance test, you should have same sieving analysis results before the crashing test and after crashing test. This is the shape of sieves here in the lab to make the sieving analysis test. As we said, if we said that probant is 2040, the first sieve is 20 and last one is 40, and the sample should be distributed between this first and the last one. Less than 90% is not passing from the first one and passing from the last one. This chart is explaining the probant concentration and the perforation diameter. This is important because of what? Because when you are selecting the probant size, you should understand what is your perforation entrance hole to avoid bridging of the probant at the perforation interval and to get early screen out. Also, something else you should take in consideration for it. So you should have, for the perforation, you should have the perforation entrance hole is bigger than the particle diameter for the probant with from 8 to 10 times. Something else also should be taken into consideration when selecting the probant size is the fracture width at the tip. The tip is the end of the frac should be bigger than the fracture width at the tip should be bigger than the probant diameter with 3 times at least. This table is showing some of the probant properties here against the closure stress. So as we said, the closure stress have a direct effect on the fracture permeability required. So we have this table to can explain what is the probant size and the probant type. So either high stress, intermediate stress for each closure stress and required the fracture conductivity or fracture permeability in darcies. So we have here the range less than 100 darcy of the fracture permeability against 5,000 closure pressure as example. Here we can use the 2040 and the 12 by 20 TPS type. Also here, if it is required to have frac permeability between 300 and 400, we can use 16 by 20 HSRCS probant type. If we wanted to have 400 to 600 darcy of the fracture permeability, we can use 20 by 40 intermediate strength probant or high strength probant. This is example. Okay, this term can explain the fracture conductivity. The fracture conductivity is can calculate it from what? From the fracture width, here the W, and the permeability of the probant pack, which is K. So also this can be equal to the fluid viscosity multiplier by the length of the back to have the term of W, which is the fracture width. We can calculate it from the length of the back of the probant and the Q of the bumping flow rate and the height and the differential pressure applied. So we can calculate this from the Darcy equation. Okay, and apply the Darcy equation to calculate the fracture conductivity. Here we can apply the Darcy law to get the K value by multiplying Q and mu by L at divide by A and delta B. It is normal Darcy equation to have the fracture conductivity, or to use this equation to have the permeability of the probant pack multiplied by the fracture width. Actually, this equation that we are using to calculate the probant conductivity for the normal fraction operation. Here we are going to discuss the factor that affecting on the fracture conductivity. First, how we to calculate the closure pressure. We can calculate the closure pressure from the fracture gradient multiplied by depth and deduct the value for bottom hole production pressure. So once we get the closure pressure, we can go to this curve here. This is the permeability, or this curve, the conductivity of the fracture against effective closure pressure for each type of the proppant or each size of proppant. So you can directly from this graph calculate the fracture conductivity if you have the effective closure stress. This is the actual graph that we get from it. This table. This table is coming from these graphs. How we get this graph here? We get this graph here by testing in the lab in this device. This device is its idea is like what? You're putting a sample of the proppant inside this test plate. This is the proppant shape, and you put the proppant sample inside this one and applying different stress on it. Once you apply different stress using these hoses, you can pump fluid through this proppant samples at different closure stress. So you can draw this curve for each type of the proppant like this curve through this testing facility. Okay, now we are going to discuss the stimulation key equipment. We will cover here in this point general overview for the equipment, high pressure equipment and low pressure mixing equipment, including blender and both system, both strict blender and BCM is hydration unit, also the monitoring unit and bulk and the storage equipment. This is the layout for the fracturing equipment. This here, our high pressure pump. This manifold consists of two manifolds actually, one high pressure and one low pressure. The low pressure is used as a discharge for the blender. The blender is used for mixing the proppant with the fluid and mixing the gelling agent, mixing of additives with linear gel. So we have here in this manifold we have high pressure manifold is discharge for the high pressure pumps to connect these two lines to the wellhead. So we have low pressure manifold work as a suction for the pumps and high pressure manifold working as a discharge for the high pressure pumps. And we have the blender. The blender discharge is connected to the low pressure manifold here to connect the suction for the high pressure pumps. The high pressure pump here, the blender here is connected to the hydration unit, and we will discuss the function of the hydration unit. And this is the sand sheave. The sand sheave is carrying the proppant and deliver this proppant to the pot here for mixing. And this is the frac tanks which contain the water and the linear gel. This is another picture, actual picture for the shape of the fracturing fleet at one of our wells in the Western Desert. This is here, this is the blender. This is the blender, this is the high pressure pumps here. This is the frac tanks here. This is the sand sheave here. And this is the manifold, high pressure and low pressure manifold. And this is the two lines that was in the previous drawing. one line here and one line here connected to the well. This is the high pressure pump. There is two types of the pumps. There is skid pumps, and this is mainly using for offshore, and there is here we can compare. This is track mounted pumps, as we can say, and this is skid pumps. This super pump, its horsepower is ranging from 1100 to 2100 horsepower. 2000 horsepower. There is two different types of these pumps. There is triplex pump and the quantuplex pump. Triplex pump have a 3 plungers, and the quantuplex pump have a 5 plungers. For sure, the quantuplex pump has a higher flow rate, and it can be used for the fracturing job that required high flow rate. Okay, we pass this slides. This is land operation for high volume. From where we can know that is for high volume, that for this tank, this is all that we are seeing here. This is a frac tanks. So there is huge amount of frac tanks that is storing the water. So because of this, this setup is for high volume. This setup is for high pressure or high horsepower. Because what? Because of, if you can see here, all these pumps are used at the same time to pump the treatment, and the fracturing tank is less than the previous setup. Here for this case, this is offshore using a barge. We are using the same equipment, but we are using different barge, installing this equipment at barge, and using this can be used not in the sea, but it can be used in lakes and swamps. Okay, this is different type of pumps. These pumps is its horsepower is 2250, and this pump have a two design. First one is a skid for offshore activity, and second one is track mounted for land activity. Also, this different type of pump, smaller than the previous one, also at the same time have skid design and the track mounted design. Okay, this is the shape of the manifold. The manifold, as we said, is containing from high pressure manifold and low pressure manifold. The size of the tubing at the manifold is 4-inch. This is the ID for the flow line. This is what we call the safety relief valve. Safety relief valve have two different types. The first one is we call pop-off. This is designed with a spring that from the top here, you can adjust the spring power or spring position to have different value for opening the port to relieve the pressure. There's another type is called GORV. GORV is using nitrogen chamber in the top of the valve to set the required pressure to open the relief valve. Also, we have a check valve in the setup, because what is the function of the check valve? Check valves are used to prevent fluid to back from the wellhead, because in case that we are during the fracturing job, once you stop pumping, there will be still wellhead pressure applied at the wellhead. This wellhead pressure, if you directly open, or there is this pressure is vented directly or suddenly, this will result in rapid flow back from the proppant to the well bore. So to avoid this situation, we are using check valves. Last thing here is the tree saver. Tree saver is used to isolate the wellhead pressure to do a rigorous job. How it is work? It is work like this. We have this wellhead is passing here from through the Christmas tree, and have a cups below to sit inside the casing to hold the pressure from the bottom. So each cup, it is inflatable and open inside the casing like the BOB tester cap, and isolate the Christmas tree to work to do the fracture job at pressure rating higher than the rating of the wellhead of the Christmas tree. This is the connection of the flow line of actual fracturing job. Here we have the frac gate valve. This is gate valve with the controlling. This is the first controlling valve at the frac string. Also, we have is connecting through treating iron, 3-inch treating iron to this valve. This is the what is this? This is valve is this. We have these two ports, as we said. One of them install the relief valve on it, and another one is we installing the pressure transducer to get the fracturing pressure during the job. Here we are installing the two pressure transducer, and here we are installing the bleed off line. This is manual bleed off line, and this one is we installing the pressure relief valve. We are installing the pressure relief valve here, and we are installing another line for bleeding manually through low torque valve here. So we are installing here one relief valve, and here we are installing the gas operated relief valve, which is GORV. Here two pressure transducer, the check valve is installed here. Okay, this is the back side. This connected to the annulus. If we are going to use frac string with backer, this connected to the annulus to applying pressure during the job at the backer to avoid moving the backer from moving up due to applied pressure from the bottom. We have here the pressure transducer. We have here normal valve, and this adjustable choke thrust in case it is required. We have here the mixing equipment. We have here the BCM or hydration unit. The function of the BCM or hydration unit is to mixing the gelling agent as a flying additive. Normal operation, we are mixing. We do the batch mixing of the gelling agent on the water inside the frac tank before starting the job. So we are mixing the gelling agent before starting the job. So what we are mixing before starting the job, we are mixing the biocide, we are mixing the salt for shell inhibition, we are mixing the gelling agent. So we created what we called a linear gel. Then we use this linear gel to pump through the blender and mix the flying additives. What is additives are mixing flying? The proppant, the crosslinker, the breaker. With using this BCM or hydration unit, we can use it for pumping of the gelling agent in fly. So we are just mixing water with salt before the job, and everything else is pumping flying during the job. Okay, the blender itself, this is the shape of the blender. What is the blender design? We will go through with details a little bit. We have two manifold in the blender. Two manifold is like this. with different ports. These two manifolds are high suction manifold and discharge manifold. The suction manifold is work as suction from tanks to the blender. The discharge manifold work as connected to the low pressure manifold and the manifold as a suction for the high pressure pumps. So also for the blender we have centrifugal pumps to suction as the suction manifold to pump the fluid from the frac tanks to the blender. Also we have flow meters at the suction manifold to measure the flow rate of the linear gel during the suction from the frac tanks. And we have densometer. Densometer is measuring the dirty volume after mixing the proppant, because we cannot use this normal flow meter to measure the flow rate after mixing the proppant, because this working with the turbine. This flow meter is working with turbine. If you passing the frac fluid with proppant through this turbine, it will be damaged directly during the job. So we have to use densometer. Densometer is measuring the flow rate with effect of gamma ray. So we can measure the density and the flow rate. So we are measuring the volume of the proppant, the BBA, which is the proppant concentration, also, and the flow rate passing through the densometer to the suction manifold or the low pressure manifold as a suction for the pumps. This is a mixing tub. This is a mixing tub working as this is what we use for mixing all the additives at the blender, to mix all the additives with liquid and the dry additives like proppant, and the liquid additives like linear gel, breaker, crosslinker. This is the sand screw. We are using this sand screw to get the proppant. The proppant is moving at this sheave, from sand sheave to this hopper. Then with sand screw, we are using this sand screw to move the proppant from the hopper to the mixing tub. This is the liquid additives pumps. We have a lot of pumps on the blender to get the liquid additives from each tank to be pumped flying on during the job. This liquid pump is connected to the mixing tub with these hoses. So these pumps are pumping the fluid from the added fluids from each tanks to the mixing tub directly. Okay, what is the blender function? Blender function is dependent and efficiency single system. It is manually or semi-automatic operated, and we are using this blender to use it for optimum proppant placement. Okay, and to guarantee the fluid quality of the mixing with the required concentration. Also, we are using the blender for automatic response to unplanned rate change, because it have a software to control all the pumps and the sand screw and the mixing tub, so you can guarantee the concentration of the additives pumped during the job. You just select the concentration that you want, and the software will operate the pump to pump with the required rate, and also give you a measurement for the actual concentration and the actual pumping rate for each additive. Also, it should be communicated with the frac cat. The frac cat is the unit of controlling and monitoring all the activity during the job. Also, it is measures the slurry density and calculation, use new suction and discharge flow meter and densometer. As we said, it is used to process and control liquid additives, flow meter, and it's accurate from 1 to 35 gallon per meter. Also, it is process and control the dry additives like the proppant. Should provide also totally independent hydraulic backup system in case of failure during the job. You should have an independent hydraulic system to be backup during the job to avoid any stop during the activity. This is the monitoring unit. This panel is the monitoring is the control panel for the pumps. Here, each one of these panels, here we have 8 panels, one for each pump. You can control the pumps from this unit. Also, you have here, this screen is showing you, and you control from this screen the rate of each additive during the job. This is monitoring and controlling cabin. Here, this is the control panel for the pumps. Okay, this is where the room that we are monitoring the additives at the controlling room to show you the concentration of each additive and control the rate of each single additive at the blender. So you can control the pumps and the blender from the control room. This is this picture is showing the rule of each one of inside the control room. This guy is a frac engineer. So those two guys are the client witness, and this guy is a frac master. So the frac master is the manager of the job, as we can say. These two screens is the client digital graphing monitoring. Okay, we have here the logistics, as we can say, the tanks. This is the frac tanks. This can be used as a diesel tank. This one is nitrogen tank. This can be used as a frac tank, but this tank is smaller than this tank. This tank capacity is 500 barrels. This one capacity is 150 barrels. This is the ship for the sand sieve here. This is logistics. This truck can used as a transportation truck for the sand, and can be connected directly to the blender through this port. Also, with same function here, this sand sieve is used instead of using sheaves here, sheave to transport the sand from the hopper at the sand sieve to the hopper of the blender. We can use this to avoid any mechanical parts. Just with gravity, we can connect this truck to the blender to avoid any failures during the job due to the mechanical moving parts. Okay, we just finish our topics today. Another thing I need to explain, because yesterday we have a question about how we can calculate the rock properties from the sonic log. I have here one slide. I will stop sharing this one. Here we have this small table that can showing us how we can calculate either Poisson ratio or shear modulus or Young's modulus or bulk modulus from the sonic log. First of all, we should understand that to use the sonic log to calculate the rock properties, we should use the dipole sonic. Dipole sonic is recording shear wave travel time and the compressional wave traveling time. So first of all, you should calculate the Poisson ratio from this equation by dividing the shear wave traveling time by the compressional wave by using the shear wave traveling time and compressional wave traveling time, then you can calculate Poisson ratio. Using the results of Poisson ratio, we can also use this data to calculate the shear modulus using of the bulk density and here the shear wave. Okay, then we can calculate Young's modulus from the shear modulus and Poisson ratio here. Then we can calculate the bulk modulus using the bulk density and shear compressional wave traveling time and shear wave traveling time. Okay, any questions?
Thank you, Engineer Ahmed Samir, for this very informative webinar. I'm sure the audience benefit greatly from it. We have a few questions for a quick Q&A session, and I have collected a few questions. So we have our first questions. Our first question is asking how the pressure of the closure is calculated before choosing the type of the proppant.
As we said yesterday, we are calculating the effective. One second. Here we calculating the we calculating the closure pressure here from this equation. From the fracture, we can calculate it from the fracture gradient, or yesterday we give another. This is the most rapid way to calculate the closure pressure. We use the fracture gradient in the area, if we have it, multiply by depth and deduct the bottom hole flowing pressure. Or we can use the equation that we explained yesterday here. To get the effective stress. Effective stress is calculated from the total stress and deduct the pore pressure after multiplying by pore elastic constant. This stress is equal to the closure stress. Okay.
Okay, thank you. We have another question. What are the most important data to take into account when choosing the composition of fracturing fluids? And how we calculate the amounts of the different components according to this data?
As we said, each one of these additives have a certain function. So you should first of all have XRD to have a composition for what minerals that you are having inside your reservoir rock. So if we have this XRD and you have a mineral composition for your reservoir rocks, then you can decide each one of the additives that you are want, each type. So as an example, if you have a certain type of clay and this clay is sensitive to the water that you are going to use, so you have to use clay stabilizer. Normal. So also, if another test should be done before selecting the frac fluid is the compatibility test. You should make a compatibility test between the fracture fluid and the reservoir fluid to see if there is any undesirable undesirable material that will be precipitated, or there is emulsion will created or not. So if there is emulsion will created, you have to select surfactant or non-emulsifying agent to break this emulsion. Its concentration should be decided inside the lab. So what is the required concentration of non-emulsifying agent to prevent formation of the emulsion? So the concentration of non-emulsifying agent should be selected in the test, during this test. Also for the gelling agent concentration and breaker concentration selection. How we are selecting the gelling agent concentration? We have our reservoir temperature, and we are designing the frac fluid to have minimum viscosity to carry the proppant according to the proppant selection. So you are doing a test in the lab. We have a chart with viscosity of the linear gel in the room temperature should be equal a certain value to have the required viscosity inside the reservoir pressure inside the reservoir against the reservoir temperature. So it's work like this. You will have a sample from the mixed fluid with the gelling agent, and it should show certain value of viscosity. This means that your concentration of the gelling agent is correct. So once this, you are measuring the viscosity of the linear gel at the room temperature, but from these charts you know that this viscosity will be equal to the required viscosity at the reservoir temperature. Because of by this way you can select the gelling agent concentration. Also for selecting the concentration of the breaker, it should be done on actual conditions. So you have a fluid bath with temperature equal to your reservoir temperature, and try different concentration for the breaker on cross-linked gel sample and measure the time of breaking. So you decide the concentration of breaker according to the result of this test. With different concentration of the breaker, you will have different breaking time. You will select the correct concentration of the breaker according to your time, the breaking time required. So as we normal, if we have one job that will spend 1 hour for bumping, so you should have a safety factor at least half an hour before the cross-linked gel start to break. So you should have a breaking time at least 1.5 hours. So you will select the concentration that achieve the 1.5 hour of the breaking time. This is how we select the fluid additives.
Thank you so much. Another question, why do we always use 2 proppant sizes during the frac operation, like 16/30? However, using one size only gives higher permeability and conductivity.
No, 16/30 not means that we are using 2 sizes of proppant. We are using proppant size ranged between 60 and 30, because it is impossible in the actual condition to have a single size proppant. So we define range. So 60/30 does not mean it is two sizes. It is range of sizes.
Okay, it's clear. Another question, how to guarantee a good distribution of the proppant, and how we can check that proppant is being distributed well?
To guarantee good distribution for the proppant inside the frac, there is different controlling parameters control the fracture distribution inside the well. First, the pumping rate. Also, the viscosity of the fracture fluid. Second, the Proppant specific gravity. All these parameters are controlling the distribution. So, as example, as much as you select lighter weight Proppant, it will be easy to carry by the gel and it will be distributed very well inside the frac. Also, the fracture widths playing a key parameter in the fracture, the Proppant distribution inside the frac. As the widths is increased, the Proppant distribution is better. So you should apply high net pressure inside the frac to guarantee good fracture widths to have a better pressure Proppant distribution inside the well. Also, the viscosity for the frac fluid itself. As you guaranteed high carrying capacity and high viscosity for the frac fluid, you will guarantee more better distribution for the Proppant inside the fraction. Okay.
Okay, thank you so much. We have two final questions. How to calculate the frac gradient from the Minifrac?
Actually, from the Minifrac, you get the most accurate value is the closure pressure, closure gradient, not the frac gradient, because the frac gradient is calculated according to what is the difference, first of all, between the frac gradient and the closure gradient. The fracture, to frac the formation, you have resistance higher than the resistance required to continue growing the fraction. We said yesterday that we have the fracture toughness, which is controlling the propagation of the frac, and this term is involved in calculation of the closure stress. And the closure stress is also can calculate it as a stress applied from the frac both sides on the fluid inside the frac itself. Okay. However, that to start initiating the frac at the beginning, you need higher pressure than the closure. So the fracture gradient is higher than the closure. Once you break the formation at the beginning, if you start pumping with 5 gallon per minute, or 5 barrel per minute, or 10 barrel per minute, and we keep this rate is constant, the treating pressure during the frac job will start to increase gradually till a certain point, then will start to increase sharply. This highest point at the data frac is the fracture point. You can calculate the frac gradient from this point. However, that you should be carefully for this, because could be effect of a changing of the rate. So because of this, I said in the beginning that we should guarantee the rate was constant at this period. So it is better to start, if you wanted to measure the fracture gradient from the data frac, to start with low rate at the beginning till you get the fracturing point, then calculate the fracture gradient. After you said that this is our frac point, you can start to increase the rate to make the data frac.
Thank you so much. We have another request, final one. Could you please recommend some of the reading materials on hydraulic fracturing?
Okay, tomorrow I will prepare some books and references to be reviewed as a reference for the fracturing, if anyone want to read in the fracture topic.
Okay.
Also, I can give it to you and you share it for them.
Okay, that sounds good. No problem at all. Okay, thank you so much, Engineer Ahmed, for answering all the questions. This concludes our quick Q&A session and our second webinar. Thank you again for this valuable and fruitful presentation. We are grateful for the time you spend to share your knowledge with us. Dear attendees, thank you so much for joining us from all over the world. Please remember to join us on tomorrow's third webinar at 5 p.m. And please don't forget to fill out the feedback form that will be attached to the email. Thank you so much. Please stay safe, healthy, and positive, and have all a great day.
Thank you.